So first talk of today is graph inference with effective resistance queries, and it's Evelyn who's going to give the presentation. Thank you, Evelyn.
Hi, good morning. I'm Evelyn. I'm presenting graph inference with effective resistance queries. This is joint work with myself, Huck, Bennett, Mitchell, and Amir. Huck at CU Boulder, Mitchell at UC San Diego, and Amir also at Oregon State with myself. So here we have graph inference, the reconstruction problem. So if we're given a graph and we have some oracle on the graph that tells us information about it, we want to figure out what the structure of this is. So we're going to characterize this by W, which is a weight of the vectors on, or a vector of the weight on all the edges. So you could do this with an adjacency matrix or an adjacency list, but we're going to characterize this with a weight vector. So I want to figure out what all of these different weights are from the graph using my oracle. So there's different options we have for a graph oracle. We could have a shortest path oracle, which tells us the shortest path between vertices. We could have an edge detection oracle or an edge counting oracle or an effective resistance oracle. This relates to random walks, which I'll explain in just a second. So for a brief history of the graph inference problem, we have some inference of trees kind of in the 70s and 80s. And then Hein in 1989 gave an n log n algorithm for a bounded degree tree. And then we have, more generally, we have graph inference. So there's some work kind of in the early 2000s around internet mapping problems that deals with this. And then we also have some a slew of kind of newer work that does this for bounded degree graphs and bounded degree chordal graphs in the case of Bastide Groenland from 2023. We also have edge counting tree inference from Raisin and ShaiFest in 2007. And we can also infer graphs from random walks. This was shown by Whitman, Schmidt, Blochel, and Theis in 2009. And then it's kind of alluded to in Spielman's 2012 lecture notes, and then kind of explored more thoroughly by Hoskins, Musco, and Sorakakis in 2018. So what is effective resistance? This is a metric on graphs that's kind of has spectral relations. So I'm going to explain more about this. It comes from physics. If you treat any arbitrary graph as an electrical circuit, you can look at the effective resistance as you would from physics. You get Thomson's principle, so it's the minimum energy unit flow between vertices, U and V. We get this monotonicity principle. If I short any edge, then it reduces the resistance between any two. Basically, the resistance can't increase if I decrease resistance anywhere. And we also have series parallel laws, kind of from circuit analysis. We have also some nice spectral properties. So we get this Laplacian formula. So we take the Moore-Penrose pseudo-inverse of the Laplacian, and we sum the diagonal entries and subtract off the off-diagonal entries. And this gives us the resistance between U and V. You can also write this as a matrix. So we get the pseudo-inverse as a graph Laplacian is this scaled version of this thing on the right-hand side, which is the resistance matrix. So that's all pairs effective resistance conjugated by this projection matrix, I minus 1 over nj. J is the all ones matrix, and this projects away from the span of the all ones vector. We also have this connection. So the total effective resistance, if I sum up all pairs, this is equivalent to the product of the Laplacian's eigenvalues. So we also get probabilistic properties. This is how it relates to random walks. So we get hitting times are this Laplacian pseudo-inverse formula as well, which means that the commute time, so this is the expected number of steps it takes to go from U to V and back to U. You can write this as this thing on the right-hand side, which is the volume of the graph, the sum of all degrees, times the effective resistance between U and V. So we can approximate the effective resistance between any two vertices by doing random walks to approximate commute time and approximate the degree sum. I divide those, I approximate the effective resistance. Okay, so effective resistance-based inference, this is alluded to in Spielman's notes. We know that to this matrix equation, there is a unique solution, which might not be immediately obvious because it's a pseudo-inverse, but because it's a graph Laplacian, we get that there's exactly one unique solution. This requires n squared ER queries because we need the whole matrix R to do this. So then we have Hoskins, Musco, and Sorakakis from 2018 who explored this more thoroughly. So they show that you can find kind of a optimal, which I'm using a little bit loosely here, approximation of the graph using subquadratic number of queries. You can also do the same with kind of a noisy query model, which is what you can simulate via random walks. So that's what they show. So we ask, what can subquadratic queries tell us more generally? So we answer kind of a bunch of different problems. So kind of some of the more basic ones are we can test for whether there's a cycle present. a cut vertex, a cut edge. That's these results here. We also do some property testing algorithms like the biconnectedness and edge detection. So those are kind of approximate versions of decision problems. I'm going to focus on this one, K completion. And so we give a tight bound for this on query complexity, and we also give a polynomial time algorithm for this. So this is the problem of graph K completion. It's inference with partial knowledge. So if I'm given a graph that's hidden to me and some weight vector that I don't know, and then I have a partitioning of all the pairs. So K are the known pairs and U are the unknown pairs. Then with size of U queries, I can get the entire graph. So I do this by solving this optimization problem. So I want to minimize this function f, and this left term is just the inner product of x, and x is just a vector of kind of the canonical completion of the graph that we're doing. And so x is going to be dimension size of u. And then so we have the inner product of that with our queried effective resistance values. And then on the right-hand side, we have the log determinant of the inverse of the regularized Laplacian based on our completion of the graph x. So we're going to optimize this, and we're going to get exactly the graph that we want to reconstruct. So how do we show this? Well, we have a lemma. So given L restricted to our known index pairs and the resistance matrix restricted to our unknown index pairs, there's one unique graph which satisfies this. And so how do we prove that? Well, we have another lemma. So for any index pair, we have that the derivative of f with respect to that pair is exactly the difference between our queried resistance and the resistance that you get on that pair, assuming that x is your completion. So if we look at the gradient here, we see that it's the difference between the vector of the queried resistances and the resistances you'd get based on x. So when those agree exactly, we have that the gradient is 0. And by the strict concavity of this function, we have that this is unique. So we have that adjacency and effective resistance vary independently from one another. So we have this lemma, which I've kind of modified here. Now I say there's either no solution or one unique graph. And the reason for this is because we can ignore the case where there's no solution, because in that case, you have a bad input and your resistances don't actually match the adjacencies you were given. So what's known is there's bijections between the weight vector, the graph Laplacian, and the resistance matrix. What we show is that there's a bijection between the weight vector and kind of this partial information on the Laplacian, partial information of resistances, where they complement each other exactly. So that's what I mean by varying independently. So the algorithm here is we query all pairs of unknowns. We use any kind of convex optimization algorithm to get the exact point. And in the case of an unweighted graph, you just use epsilon smaller than 1/2, and you just round to 0, 1. Or in the case of a weighted graph, we get an approximation algorithm. So here we're using the information with our queried missing entries, and we're getting the weights factor. So the function L sub k of x maps the completion of the weights to the associated graph Laplacian. And then this function maps those to a real value in a way such that the gradient is exactly the resistances you get, assuming that's your completion. So what's the query complexity? Well, we get O of k by design, right? And then we get theta of k by an adversarial example. So if we take this kind of star graph with triangles appended everywhere, and maybe my adversary is selecting one branch to modify, then I need at least k different queries, because I need to sample one endpoint in one of these triangles for each of them. So that's how we have a tight bound on the query complexity. So we also have the running time complexity. This runs in polynomial time, and that's because the function f of x is the self-concordant function. And to see this, you can just note that this, if we're derivating with respect to one of these, this is going to disappear by the second derivative. And we have that this function right here is just a composition of a self-concordant function with an affine function. So we know that the function overall is also going to be self-concordant. So in conclusion, we know that we can infer a lot of different graph properties. We can reconstruct, we can complete using effective resistance queries. We can also detect various versions of connectedness and adjacency. So we have that with a minimal query complexity, we can do completion of the graph, and we get an approximation algorithm for weighted graphs and an exact algorithm for unweighted. And it's exactly the uniqueness proof that gives us this optimization algorithm, which is kind of neat. And for future directions, we know that full subquadratic reconstruction, which we do given a tree decomposition, but we want to maybe do this without a tree decomposition for some fixed class of graphs, could be interesting. We also want to reconstruct a simplicial complex under an ER query model, which we have reason to believe is possible. And then we also kind of have this other idea where this completion algorithm gives us an idea for an online learning algorithm where we can reconstruct a graph kind of as it appears or as it's built. So this would just involve completing the graph each time you add a vertex. Yeah, so that's the end of my talk.
Thank you very much, Evelyn. We have time for a couple, maybe one quick question. Not surprising.
I guess maybe two even related questions. One, is there any hope for non-adaptive algorithms where you just do your queries upfront, like randomized? And maybe two, you prove these things via showing that the solution is unique. Is there ever a gap where you have like an efficient algorithm in terms of query complexity, but not in terms of running time? Because sometimes this unique solution may be hard to find.
Yeah, great questions. So regarding the first one, we have, I referenced, where was it? Sorry. Referenced this paper, Kanan, Matthew, and Zoe, 2018. They give a O n to the 3 halves algorithm for bounded degree graphs. We have kind of an analog class of graphs where we give kind of an adaptation of this algorithm, but so that's kind of a randomized reconstruction algorithm. But we kind of, we don't have a great way of describing this class of graphs just yet. So we do that. And as far as non-adaptive, that's a good question. The answer is I don't know.
Thank you very much.
Okay. Hello, everybody. For those of you who haven't met me, I'm Szymon, and today I'm going to tell you a little bit about embeddings that preserve the neighborhood structure of the input. So before I kind of get into all of that, I just want to zoom out a little bit, and I just want to talk about like metric embeddings in general. So what we're trying to do is we have some sort of endpoint data with some given metric structure, and we'd like to embed this into a useful space. And just for the purpose of this talk, we're going to just focus on embedding into Euclidean space. And ideally, what we'd really like to do is we'd like to preserve all the distances exactly, so something like isometry. But in kind of a wide variety of circumstances, this isn't really going to be possible. I mean, you can construct like even 4-point metrics that aren't going to embed into Euclidean space. So we know this is not possible. But what we do is we relax, and it gets a little easier, and we do near isometry and low distortion embedding. And generally, this becomes feasible. But for a lot or a few instances, this is still kind of too strict a definition. In particular, for data visualization, where we'll try to take some arbitrarily high dimensional, arbitrarily large data set and try to visualize in just 2 or 3 dimensions, we know that near isometry is going to be too strong, and we can't expect to do it in such low dimensions. So in lieu of this, these algorithms focus on something qualitatively weaker. They focus on just trying to preserve neighborhoods. And that's kind of going to be the focus of this talk. So we're going to study, in particular, neighbor-preserving embeddings, which for some notion of neighbors, the goal will be to kind of keep our neighbors close and keep our non-neighbors separated by some amount. Now, to kind of set our expectations, I want to talk a little bit more about near isometry. So if we'd like to do near isometry in general, we're going to want about log n dimensions. We're going to kind of be stuck around that lower bound. Most famously, we see this from the Johnson and Lindenstrauss lemma, which tells us that, you know, if we have any Euclidean subset, applying only a small amount of distortion, we can always bring it down to log n dimensions. But unfortunately, that's kind of as far as you can take it, and we have strict lower bounds. We also have like another result from Bergam that tells us we can also do this for an arbitrary metric space, except we have to pay a little bit more in the distortion. But even so, we're kind of still stuck at log n. So given that I'm kind of studying data visualization, these embeddings are going into just 2 or 3 dimensions, and I'm studying a relaxation of near isometry, the general question is, can we go beyond this log n barrier under this kind of relaxed paradigm? And yes, n is the number of points, sorry. Yeah, n is the number of points. So I'll kind of cut to the chase here, and I'll tell you that unfortunately the answer is going to be no. We're going to actually recover a very similar lower bound. But before I kind of get into the messy details of that, I think I owe to you guys to explain what exactly do I mean by neighbor preserving embedding. So first, we need some notion of neighbors. This we're just going to formalize as a graph. So we assume that our endpoint subset has some graph over it where any 2 points share an edge if they're neighbors and no edge if they're non-neighbors. And given this graph, we say that some embedding into Euclidean space is going to alpha neighborhood preserve, or for short, because I'll say this a lot, alpha preserve the graph if it does two things. Firstly, for any 2 points that are neighbors, we'd like to keep them close. So for any u, v that are neighbors, we'd like to keep them within some bound distance like 1. And for any 2 points that are non-neighbors, we'd like to keep them some minimum distance apart. And here we're going to introduce this parameter that we can play with, kind of similar to like D in distortion embeddings. But something that's interesting that you should know is that we're going to actually see that there's going to be a phase shift, especially in the difficulty of this paradigm based on how we set this parameter. In particular, you'll notice that if alpha is greater than 1, the graph will be exactly recoverable from the embedding. This is kind of not hard to see because all our neighbors will be less than 1 and all our non-neighbors will be greater than 1. So just doing pairwise distance comparisons, you can recover the graph precisely. But it'll turn out this will be quite difficult to do in practice. So we'll also focus on the alpha less than 1 case where there might be some overlap between our neighbors. So we're not guaranteed to recover the graph, but it's going to turn out to be at least a lot easier. So let's focus on this easy case first. So what you can prove is that for alpha less than 1, take almost any endpoint neighbor relation. And if you want to embed it in the Euclidean space, you're going to need at least log n over log 1 over alpha dimensions. So kind of recovering that same log n bound we saw from something like Johnson, Linden, Strauss, and other kind of near isometry results. And we also have a matching upper bound. So in general, it's going to be, from a dimensional perspective, it's going to cost us as much as near isometry. But I already told you that this kind of alpha greater than 1 case is going to be much more desirable because we'll actually be able to recover the graph. So in this case, it's going to turn out that for almost all endpoint neighbor relations, we're actually going to need dimension scaling linearly with n. So we're going to see this like exponential jump. And this is kind of strange, and at least surprised us, because n is kind of usually the bound that we associate with something like isometry, right? Take n points in general position in Euclidean space, they need n minus 1 dimensions, or Shai's embedding says that in n dimensions, you can embed any metric space in L infinity, et cetera, et cetera. Basically, what this tells us is that if you want to do this recoverable preservation, you're going to kind of pay a very similar price in terms of the dimension as exact isometry, which seems quite steep, but that's sort of the unfortunate reality, I guess. So I want to kind of leave you guys with some intuition on why this is. So I'm going to try and show a quick toy example. And I know it's been a long week, so I've tried to get it down to just 3 lines here. So bear with me, please. Basically, I'm going to show that there exists at least one neighbor relation over n points, which cannot be alpha greater than 1 preserved or recoverably preserved, and 0, 1 to the d, for d being little o of n. And so the proof goes like this. For a contradiction, suppose that we can actually embed all our graphs in 0, 1 to the d for little o of for d equal to little o of n. Then by recoverability, each graph must have a unique embedding, right? Each graph is unique. We can recover them from their embeddings, so their embeddings must be unique. And so we can set up the following very, very simple counting argument, basically, where we say, okay, then it better be the case that the number of graphs lower bounds the number of unique functions into 0, 1 to the d, right? From our endpoints to 0, 1 to the d. And so you count this, there's 2 to the d times n of those functions, and there's only 2 to the n choose 2 graphs. You rearrange, you get your contradiction, and it's proven. And this kind of highlights the basic principle of this type of embedding, where when it's recoverable, you can actually make your counting arguments much, much stronger by working with the uniqueness of the embedding. But I don't want to end my talk kind of too sad, because I already told you it's bad news that if you want to do recoverable embedding, you need at least n dimensions. So we kind of study a variety of cases in the full paper. So I kind of want to highlight one of those, and that is that there's some hope if you consider a sparse graph. And if you consider a sparse graph, you can actually get recoverable embeddings with O of log n dimensions. So kind of recovering, again, that same bound from near isometry. But turns out you're going to be stuck there. So we're still stuck at this log n. And so kind of I guess the takeaway here is that just focusing on the neighbor relations doesn't make it easier to embed in terms of the number of dimensions you need as compared to kind of focusing on all the distances. Yeah, and just before I end my talk, I just want to talk about some of the other extensions we have in the full paper. We're going to also do some bounds for embedding in general norm spaces and metric spaces, some graph-specific bounds based off like clique size and diameter and such things. We'll also focus on some graphs with special structure like cluster structure. And we'll give, of course, the matching upper bounds. Yeah, thank you. Yes. Thank you. I'm glad.
So, yeah, I have many questions. Maybe I can ask you afterwards. But
please.
One of the things that we care about, say, when we talk about learning or nearest neighbor, is we want to preserve the order of the instances rather than the length of the distances.
Yeah.
What can we say about such embeddings?
That's more for the literature of ordinal embeddings, which is already quite well studied. To be honest, I forget what the exact results are in that case, so it can be a little bit more difficult. But I think you're thinking of like k-nearest neighbors, right? Yeah, the techniques there are quite different. So I'm not sure I can speak too much on it, but
and another question about the positive result.
Yes.
What's the computational complexity? We know that like it gets close to correlation clustering, which I know is MP. How are the computationally the positive results?
Yeah, so our positive results here are kind of going to be tight in like a sense for most graphs, but they're not going to be tight for like very specific graphs. So they're usually using like pretty dumb strategies, which is why I wouldn't really call them like an algorithm. Like they're just going to look at the adjacency matrix and kind of construct a very simple embedding based off of it. So computationally, they're very inexpensive, but they're also not necessarily what I would call a good algorithm, if that makes sense. So there's still some like open work here on the upper bound side of like, how do you find a good algorithm that kind of provably does this type of alpha preservation? So yeah.
Thank you.
Yeah, I'm pretty sure. Yeah. I mean, like for instance, this bound here, you're just gonna like use the adjacency graph to kind of create some embedding, and then you use Johnson-Lindenstrauss to bring it down to log n. So it's not too. Yeah, but I mean, it's like usually like just using the adjacency graph alone can like give you already a somewhat decent embedding. So it's like you don't have to play with it too much, but we can talk about it more afterwards.
So maybe a clarifying question for the case that alpha is smaller than 1. How do you avoid like the trivial embedding?
Yeah, so like you're talking about like just embed all things so that within there. Yeah, so that obviously is like a valid embedding, and that is how we're going to get our kind of log n upper bound. I think the key point is that like you could always usually do a little bit better than such an embedding.
But what is better?
Like in the sense of like lower dimension. So for example, imagine you had like a 2-edge graph, right? You could obviously embed it, like, so say you have a 2-edge graph like this, you could obviously embed it as a triangle. That's not really a good embedding. We know that we can always stretch it out and do a lower dimensional embedding where more of the structure is kind of apparent. So like the trivial embedding does exist. It just might not be such a good embedding for most graphs. Does that make sense?
I think I need to take that.
Okay, yeah, sure.
Thank you, Szymon.
Thank you. Yeah.
All right, so this is going to be a bit of a change of pace. I'm actually going to be talking about conformal prediction. My talk is just before Vladimir Vovk's talk on conformal prediction, which is a little embarrassing. I feel like the standards are a little unrealistically high. But I hope you will forgive me if I say something somewhat inaccurate. This is joint work with Rina, who's hiding there in the back. But I thank her for getting me into this area. This is actually my first paper in conformal prediction. So what is conformal prediction? The setting is simple enough. The setting is just the standard setting where you have IID, or sorry, not IID necessarily, but covariate response pairs, n+1 of them, where the n+1 should be treated as the test point. And you want to do predictive inference. You want to produce some set that covers the test response with some pre-prescribed probability. Okay, so this is an uncertainty quantification question. There's lots of wrapper methods that do this. I'm going to focus today on something called split conformal prediction. So what does it do? It's essentially the validation analog of predictive inference. You split your data set into training and validation, really, or training and calibration. Train on the first, calibrate on the second. And how do you calibrate? You form these things called conformity scores, which are essentially measures of fit. Think of something like the absolute residual. And then you output the set where your conformity score on the test point is, in some sense, it conforms with the calibration set. Okay, so it can't be, it basically has to be less than the prescribed quantile on the calibration set. So this is the entire algorithm. It's an extremely simple one to implement, extremely impactful, and the sort of weird color thing that appears there. But yeah, so the theorem is that if the data is exchangeable, then this actually is a valid algorithm. Okay, so this is a classical result. One thing I really like about this area is that the proofs are things that you can actually teach in your undergraduate classes. So I'm just going to go ahead and prove this for you right now. So this is literally my coverage event, which is written here. Okay. The key thing to notice is that the quantile is actually super stable. So if I add another point or remove a point, it just changes the quantile, the level at which the quantile is computed. In this case, it just changes it to 1 minus alpha. Great. But now I have exchangeability. So the right-hand side there, I can change Sn plus 1 to any of the k points. Now I average the right-hand side over all the k points, but this is literally the fraction of points that are less than this quantile, which is just 1 minus alpha. This is the entire proof. And this is one of the reasons I really like this. It's very easy to describe. So hopefully in the end, I'll have some time to give you literally a proof of the result we prove. So what are we interested in? We're interested in what happens when the data is not exchangeable, in particular in the time series setting. And this could happen because, well, of course, the data could be dependent. But even if the data is exchangeable, if you use a predictor that has memory, so if you're using the previous points to predict the next point, you will kill exchangeability in the scores. So here's a simple simulation. So this is just, this is the case where there's no memory, but then the noise is correlated across time. So this is an MA process with memory T. You're just averaging over windows of Gaussian random variables. So T here is the window length. And I've plotted, oh, sorry, this is the oracle setting. So I'm just going to assume I know the underlying F and I'm using the absolute residual as my score. And I'm plotting the coverage of split conformal here. So this is as n increases, you can see you eventually get to the prescribed coverage, which is the dotted line here. But for fixed n, if T increases, you actually lose coverage. And there's kind of predictable way in which it's happening. And the important thing to notice is that it's quite modest. So you can go ahead and see what this loss of coverage is like. And it's basically linear in T over n for this MA process. Okay, so the question here is, can we capture this in some theoretical way? We'll see if we can do this for a larger class of time series models. So before I go there, let me just say that there are lots of methods for time series. There are notions of departure from exchangeability that have been studied before, but they don't necessarily behave well for time series. I'm focusing on the split conformal prediction method. And for this particular method, there's this nice paper by Oliveira et al. In 24, which basically says if your data is mixing in the following sense, if you define the beta mixing coefficient as take any subsequence of Z, stagger by tau, right? And look at the sequence where these two pieces are independent, and these two are actually close to each other in TV. So that's the beta of tau that they define, or this is the standard definition of beta. And they show that, well, the loss of coverage of split conformal can be bounded in terms of tau and beta of tau. And that's the rate that they obtain there. The constant is pre-specified, but that's really the rate. And the key to notice is that for the MA process that I defined before, this is square root T over n. Even though in the plot, we saw basically the fast rate T over n. The second thing you might ask is, well, is beta mixing really what you need? Right? Is beta mixing really even a generalization of exchangeability? So those are the questions we're going to try to answer. So inspired by beta mixing, let me define two deletions of the sequence where I put these k points in the end, stagger by tau, and put the rest in the beginning. So that's what I'll call delta 0. Delta 1 is essentially the same thing, except I'm keeping the k points from the end and the rest from the beginning. There's still a stagger. All right. So in a picture, if that's my sequence, I keep the front and the back in a certain order for delta 1, in a slightly different order for delta 2. Okay. So that's it. Now, if k and tau are in a slightly different regime, I can't really split by tau, so I have to keep contiguous subsequences. That's just a corner case. The only thing to really remember is that delta 1 always has last entry zk, delta 1k, and delta 0k has always last entry zn plus 1. That's how we've defined it with all this staggering. And here's our new coefficient. It's something we call the switch coefficient, psi for switch, which is the TV distance between delta 0 and delta 1 at any given k. And our notion of the switch coefficient on average is going to be the averaged switch coefficients over all k. So you fix a tau, that's going to give you some measure of deviation from exchangeability. For an exchangeable sequence, you can actually verify that that's 0 for every tau. So the proposition is the following. Because this is in some sense inspired by the beta mixing definition, really the switch coefficient is actually bounded by the beta mixing coefficient up to a factor 2. But it's strictly weaker because it generalizes exchangeability. It doesn't really generalize independence, right? An exchangeable sequence has psi equals 0, but it need not be beta mixing. So what's the theorem? We show that basically the loss of coverage is characterized by the switch coefficient. So there's two things happening here. First, you get the fast rate. The second, that's the switch coefficient. A couple of remarks. This is the under coverage, right? We're bounding the probability of under coverage, but you can basically turn that into a bound on over coverage. So this is really the coverage loss, two-sided. For a beta mixing sequence, you get the fast rates, right? You don't get the square root. And actually, you can ask, is this the right rate? I mean, we seem to have improved the square root. It turns out it is the right rate. So there is a beta mixing process for which the loss of coverage is indeed exactly what we show. So this is for all the pre-trained predictor, n naught was 0. You can ask what happens if n naught is not 0. So if I actually run split conformal by train validate splits, and now I have memory in my sequence in that f hat is trained not just on zi or xi, but all the other points before that. So it has memory in how we train the sequence. We run the same algorithm. Turns out the analysis, the theorem is basically robust to that setting. I've stated it here for the stationary mixing setting where you get, again, the fast rate. N is replaced by n1, and there's a lag by L. There are now two parameters, tau1 and tau2, instead of just one. There's a variant of this that you can state just for the switch coefficients. I just haven't done it because it's more complicated. And again, you should compare this with the slow rate kind of things that you get from prior work. Okay, good. So I think that basically almost concludes my talk. So I'm going to give you a 30-second proof. I've never done this in a 10-minute talk, but I just really, really like how simple this is to prove. So I'm just going to try to do it. Okay. So these are exactly two facts that I said before. If you delete things from a sequence of numbers, forget that these are random, the quantile just shifts at the level at which it's computed. This is just two such inequalities. Okay. So let's go back. This is our coverage event. Delta 0 is defined by deleting a bunch of points. That just changes the level at which the quantile is computed. First step. Second step, the right-hand side depends only on delta 0, and Sn plus 1 by definition is the last entry of delta 0. But delta 0 and delta 1 are close in TV, which means I can replace delta 0 there by delta 1, noticing that Sk is its last entry, and pay an additive psi. Average this over, I can add back the points to S, changes the level of the quantile, average the right-hand side over all k, just like before. This is the average of, this is basically the fraction of points that lie below this quantile. By the definition of the quantile, it's precisely the level of the quantile. That is the 5-line proof of the entire result. Okay, so let me not keep going. The takeaways here are the switch coefficient is an interesting object worth thinking about as a deviation from exchangeability. It seems to actually capture what you need from for at least split conformal. And this is basically avoiding all the empirical process theory here, right? It's not doing uniform convergence. It's not doing blocking arguments. It's just a relatively self-contained elementary proof. We've been thinking about how these ideas extend to things like cross-validation based methods on time series, right? Now the method has changed, no longer split conformal, but can you sort of use these ideas to analyze that and even inspire a method? There are several open questions here that I'm happy to discuss at the poster session. Thanks.
Got questions for Ashwin.
Very interesting. I wonder, here if I understood you correctly, you're talking about fixed size memory. What if the memory is just decaying with time, but it's not cut off at any point? Because we have many situations in which we take a coefficient of the past plus some coefficient of the next step, and we never chop it.
Yeah, that's a good question. I'd have to think about it a little bit more. Let me say that as stated, this requires fixed size memory, at least while training. Of course, you could have coefficients that use all of the past, like you're mentioning. I'm not 100% sure any of this would just go through as is. It would definitely require some modification. If you used, literally, if it was like a truly causal predictor that used all of the past, I'm not sure this would go through yet. Yeah. Should I take one more or?
Yeah, we can take one more.
So you're you're giving this coverage for the split conformal method, but you know that split conformal is a good method in this setting, even if you
yeah, that's a good. That's actually a very good question. I mean, is split conformal the optimal method in this setting? I mean, that's one of my last open questions here. Is there a method that gets you exact coverage that you don't have to pay anything for? I do think part of the way, even the title of the paper, is why is split conformal effective, despite temporal dependence? I think there's been quite a few observations that have basically seen that it's super, super robust. And you can see from the analysis that it's very, very robust. So is this the best method? I'm not going to make any statements about that. In fact, these cross-validation style methods can be much better in practice. But is it still a good method in that it doesn't actually suffer a bunch? I think the answer to that is yes, and this is a quantitative answer to that. Yeah.
Thanks.
Okay, thank you. So fortunately, Ashwin introduced conformal predictors, so I will not be doing that. My discussion will be at a high level. So it's about mainly the relation between two assumptions. One assumption is, I call it randomness, which is it's a slightly old-fashioned expression. What I mean is ID. I mean ID. So randomness in this talk just means ID, like in books on statistics in the 1950s. So people were using this language. Okay, so there is one assumption is exchangeability. Conformal prediction depends only on this assumption. Another assumption is randomness. The data is ID. This is what people in machine learning are willing to accept. These assumptions are very, very different in the situation I'm interested in batch prediction. So you might suspect that because of this difference, maybe conformal prediction is losing something. It doesn't use the full power of randomness. So maybe you can do something better. So first, let me discuss the difference between the two assumptions, randomness and exchangeability. So for infinite data sequences, or if you don't know the length of your sequence in advance, the difference between the two assumptions essentially disappears by Definity's theorem. Okay, so exchangeability means that if you swap two observations, the distribution doesn't change. And randomness, yes, as I said, it's ID. So by Definity's theorem, every exchangeable distribution on the set of all infinite sequences is a mixture of ID distributions. So which means that if you are testing randomness or exchangeability, it doesn't matter what you are using, any of statistical tools like critical regions, p-variables, or e-variables, it's a slightly newer method, you will get the same results. If you can reject randomness, you can reject exchangeability as well. But the situation changes drastically when we talk about finite sequences of a fixed length. So suppose you are given some training set, and you would like to predict the test object, the label of the test object. So you can try different labels for this test object and see how likely, how plausible this augmented training set is. So here, suppose capital N is the length of the sequence we are interested in, such as this augmented training set. So so first, you can see that exchangeability is much weaker because exchangeability is very easy to enforce in practice. You are given any data sequence, you permute it, you get exchangeability. But of course, it's not ID. It's only exchangeable. So the difference, it's clear. The difference must be big. And there is a set, a very simple set, like you take observations in the set numbers from 1 to n, and suppose you get all different observations of length n. So there are no repetitions. So this sequence, if you take a random sequence of this in this set, it will be exchangeable. It will be random in the set of all permutations of this sequence. But it will not be ID. So if you find its largest probability under all IID distributions, so it will be exponentially small. It will be like e to the power of minus n. So here I wrote the expression, the probability that all these numbers will be different. So it's tiny. It's e to the power of minus n. And in conformal prediction, for example, so you can play only on p-values of size 1 over n at least. It's 1 over n or bigger. So we can see this difference between exchangeability and ID. It completely dwarfs the differences that are important in conformal prediction. Since the difference is so big, maybe we are losing a lot. Okay, so this is the topic of my paper in the preceding. So I will be talking about conformal prediction at a high level. So one way to view conformal prediction. So Ashwin gave some picture. So another picture, which is equivalent, is that conformal prediction gives a p-value for each potential label for your test object. So you get those p-values, and if the p-value for some y potential label is very small, it means you don't believe this y can happen. It doesn't look plausible to you. So you can reject it, and it's not in your prediction set. So conformal prediction, you can regard it as a method of producing a p-value for each potential label. There is also conformal e-prediction, where you produce e-values instead of p-values. So an e-value, the requirement of validity for e-values is that under randomness, the expectation of the e-value at the true label should not exceed 1. So it's some alternative to p-values, which is mathematically, in many cases, much more convenient. And it's more convenient in the context of this paper. So in my paper, I consider both cases, p-values and e-values. But in this talk, let me talk only about e-values. So a large e-value means implausible. So it's opposite to p-values. For p-values, small means it's unlikely. For e-values, large means unlikely. Okay, so let me make a few remarks about conformal versus PAC. So there were lots of talks using PAC theory. So why do we need conformal? So one motivation behind conformal prediction is that PAC theory, in some respect, it requires too much. So it depends on two parameters, epsilon and delta. And if you express epsilon via delta, the dependence on delta is extremely pleasing. It's logarithmic. It's like log 1 over delta. And it's just too good to be useful in many cases. So if you apply typical PAC bounds to some standard benchmark data sets, in many cases you get the bound on the probability of error exceeding 1. So it's not useful. So this doesn't happen with conformal prediction. Conformal prediction, it has some guarantees of validity, but they are much weaker. And since they're much weaker, they are more achievable. So when you do PAC theory, your results are conditional on the training set, which is very good. But why should they be conditional on the training set? In conformal prediction, the basic results are marginal. If you want to achieve conditionality, it's a separate topic. And maybe you want to be conditional on the test object or the test label. All these are valid kinds of conditionality you might want to achieve. Okay, so it's some advertisement for conformal prediction. So let me, maybe I will not even state, since I don't have much time, I will not even state my main result, but let me tell you, give you some feel of it. The difference between randomness and exchangeability is huge. But suppose we are interested in what I call here prediction proper. In prediction proper, so it's opposite to something like anomaly detection. So suppose you have the true sequence, the training sequence plus the test observation. So I will assume that it's ID, the sequence with the true label. And now I want to predict. I want to exclude some false labels. The true label is not under my control. the e-value is not going to be large because of its validity, I can't control it. But what I can control is the e-value for the false labels. I want them to be as large as possible. So it turns out that conformal prediction, conformal e-prediction is as good as general prediction, which is valid under randomness, if you assume that the true sequence is ID. Under this assumption, you can show that they are close. So I can have some, this is, okay, so this is the result. So please consult the paper for it. But let me tell you how you, so it's, the result is constructive. So if you are given some predictive, which is valid, which produces valid e-values under randomness, you can turn it easily into a conformal e-predictor. So the formula is there. It's computationally efficient. So you take the e-value for the sequence and you divide it by the average of all permutations. So what you get is valid under exchangeability. You might lose something. But the main result says you don't lose much. And a similar result was stated early in 2003 in ALT 2003, but it was in the language of the algorithmic theory of randomness. So it depended on some unspecified constants. So this result is very specific, no unspecified constant. It has this constant e to the minus of 1, but this constant is optimal. You can't avoid it. Okay, so there is a very nice book by Rina and co-authors on conformal prediction. But in our book, we have in section 13.2, we discuss peg bounds for these, for different benchmark data sets. So what I mentioned earlier. And this is the paper in ALT 2003 in the language of the algorithmic theory of randomness. Thank you.
Maybe one quick question?
Yeah, it's very interesting. I mean, I wonder if we don't allow repetitions, like if I'm in the realizable case, I can throw away repetitions. Does it make IID closer to exchangeability? We sample without repetitions, which in some setting of learning, like realizable, it's good enough. Does it make exchangeable closer to my?
Maybe I'm not familiar with this setting. So here I was only comparing just to straight IID.
Well, thank you again, Vladimir.
Perfect. All right, so can you hear me? Yeah. This is Diego. Today I'll be talking about a Martingale kernel to sample test. I sadly take no credit for this talk. This belongs to Amir, who is currently doing a postdoc at U Chicago, and Aditya Ramdas, who is faculty at Carnegie Mellon. All right, so today we will be talking about this Martingale MMD. We'll start refreshing the usual kernel to sample test, and then we'll actually talk about the Martingale kernel to sample test. We'll discuss some of the properties, and I'll show you some experiments and some extensions. Okay, so first things first, let me refresh the classical two-sample test where we consider independent samples from P and Q. And we would like to test the null hypothesis that P equals Q. Okay, so there exist many different alternatives to conduct such a test. We have classical non-parametric tests such as Kolmogorov-Smirnov, Min and Watney, Wilkerson, and so on. And we also count with a number of multivariate extensions, going from geometric graphs to energy distance, ball divergences, and I could go on forever. In particular, kernel-based methods are powerful. They're very general. They can be applied to non-Euclidean settings, and hence they have become a very popular alternative. All right, so again, we have the null hypothesis that P equals Q. What does the so-called maximum mean discrepancy or MMD do. So we need a reproducing kernel K and the associated reproducing kernel Hilbert space, and the MMD is defined as the norm of the difference of the kernel mean embeddings. Great. All these kernel methods end up relying on this so-called kernel trick, which means in order to evaluate the MMD, we only need to evaluate the kernel. And in particular, the square of the MMD is going to be the expectation that we have right here. And we can separate the evaluations of the kernels in within sample and between sample. Okay, so now the question is, how can we construct a test based on this definition of the MMD? So one choice we have is to replace this expectation by the empirical average. And this is the classic MMD test statistic. And there's a very big question, which is, okay, you've given me a test statistic. Now, how do we actually calibrate the test? Okay, and it turns out that this is kind of tricky because we could use concentration inequalities. The main drawback of using concentration inequalities is that they're usually too conservative, and hence the power of the test is not as big as we would like. We could also use the asymptotic distribution of the MMD, and this is actually what is used most commonly, but it turns out that the MMD multiplied times n converges in distribution to a weighted sum of chi-squared distributions, which is in particular intractable. So in order to know when to reject the test based on this asymptotic distribution, we need a lot of intensive resampling. And in particular, alternatives like moment-based parametric approximations lack consistency or accuracy guarantees. All right, so what the authors of these papers propose is a Martingale modification of the MMD test statistic. In particular, it's going to be asymptotically Gaussian, as opposed to asymptotically weighted sum of chi-squared distributions. It's going to be easily implementable, and we're going to lose a bit of power, but not too much. So we count with comparable power with respect to the original MMD. All right, so what do we actually do? We can express the MMD on its variational form as a supremum over a ball in the reproducing kernel Hilbert space. And the element that actually achieves the supremum is called the witness function. And it can be expressed as the difference in the kernel mean embeddings normalized by its norm. So the core idea of this paper is to, of course, this witness function is unknown. And the core idea of this paper is to sequentially estimate this witness function. So at time t, we're going to use all the samples until time t-1 to estimate the witness function. And then we're going to evaluate at time I the embeddings with the inner product of this witness function that we've estimated until times I, and we're going to take the average of that. And that is Tn. All right, it's very easy to see that under the null hypothesis, the following sequence is actually a Martingale difference sequence. And that is because under the null, the expectation of the right-hand side of the inner product is 0. Okay, so we're going to take Tn, defined as above, and we're going to normalize it by the empirical quadratic variation. And it turns out that this eta n is going to converge to a Gaussian distribution, which means if we want to build a test based on eta n, it suffices to reject the null if our test statistic is above the 1 minus alpha quantile of a standard Gaussian distribution. And that's going to be our test. Okay, so again, the theorem or the test works because the distribution of eta n converges to a Gaussian distribution. In particular, the CDF converges uniformly to the CDF of a standard Gaussian distribution. Now, the authors were also able to prove that under the alternative, the test is consistent. That means that the expectation of 1 minus the actual test goes to 1. And they were also able to prove this asymptotic normality under the alternative. And it's worth noting that the results extend under very mild assumptions to settings where the kernel can depend on the sample size, The space can depend on the sample size, the dimension can depend on the sample size, and even the distributions can depend on the sample size. So none of these quantities have to be fixed in order for the theorems to go through. All right, so we love experiments in this conference, so I'll go ahead and show you some experiments. So we compared the Martingale, or the authors compared the Martingale MMD with the classical quadratic time MMD and other efficient versions, which include the linear time MMD, the block MMD, the cross MMD, and a sequential version of the MMD that is done by betting. Okay, so the takeaway from this slide is that the classic quadratic time MMD is the MMD version that is the most powerful, probably unsurprisingly. And then we have both the Martingale MMD and the cross MMD in terms of power, and the remaining efficient versions of the MMD show less power in practice. And it's also worth mentioning that the computational cost of all these efficient alternatives is way below the computational costs associated with the original MMD. Great. And some extensions, just to touch upon them. The authors also define this hybrid test statistic that goes from the original MMD to the Martingale MMD. So we can define a modified test statistic parameterized by gamma. If gamma is 0, we recover the classical MMD. If gamma is 1, we recover the Martingale MMD that we just talked about. And the authors were able to prove that this test statistic is minimax optimal if gamma is from 0 and 1/2. However, it remains yet to be understood whether this is also optimal if gamma is in between 1/2 and 1. And they leave this as future direction, but they want to emphasize that empirically, it does show near optimal behavior for all the ranges of gamma in between 0 and 1. And one last point is that because we have this convergence to a Gaussian distribution, if we take a quadratic combination with different kernels, that of course converges to a chi-square distribution. So we can combine different kernels in our test statistic, which may actually boost the performance of the test. Okay, and I think that's all from me. I thank you all, and I'll try to answer questions from this way.
Are there any questions for Diego? Yeah, I know, I'm looking, but well, it's your birthday.
Okay, so yeah, if I understand it, it's all about asymptotic convergence. I mean, but for a test, I want to know what is happening after finitely many examples. So are there any finite bounds here? Finite size sample bounds?
Yeah, that's a good question. We should probably ask the authors. As far as I know, there are not, although don't quote me here. These results, so the main theorem relies on using the Martingale CLT. I would assume if you have some Berry inbound, then you can start thinking about finite sample guarantees. But I don't know if they explored such a direction.
I was also wondering whether, I really don't know this area at all, but it could be an interesting question sometimes to kind of predict if you have two moving distributions, if they will converge to the same thing, and if so, when? Like, is that an interesting line of research, or has there any work been done to try to predict as precisely as possible when will they converge to the same thing?
So two different distributions that are getting closer to.
Yes.
Yeah, that's an interesting question, because I guess we usually think about null hypotheses that things are the same and then they depart, such as in change point detection. I guess we would have to frame the problem inversely, which would be interesting. Yeah.
Thank you.
Thank you. Yeah. So I'm sorry you have to keep up with me for 10 more minutes. I'm actually excited to present some of our work now. Hopefully, I'll be able to answer the questions a bit better. All right, so this is joint work with Tomás González, who's also doing a PhD at Carnegie Mellon, and our PhD advisor, Aditya Ramdas, who was also an author of the previous talk. Okay, so I'm going to be talking about vector value self-normalized concentration inequalities beyond sub-Gaussianity. I know everyone's extremely happy to hear about concentration inequalities before lunch. For that, let me go ahead and tell you the problem statement before I give you some motivation. So we're going to be working with two stochastic processes. One of them I'm going to call xt, the other one I'm going to call epsilon t. So xt is going to live in a Hilbert space, epsilon t is going to be real valued. And they are such that there exists a filtration ft, fulfilling that xt is ft minus 1 measurable, epsilon t is ft measurable, and the conditional expectation on the past of epsilon t is 0. Informally, this means that we're going to be playing rounds. At round t minus 1, we're going to choose xt, which, for instance, in the bandit setting, that's usually understood as an action. And then we're going to see some noise epsilon t, and this is noise because its expectation is 0. Okay, so now the question is, we can define a self-normalized process. So if we take the covariance matrix or operator of the xi's, and then we take the Martingale sequence mt, which is the sum of the product of xi and epsilon I, then we can think about this self-normalized process right here, and we can wonder if we can give concentration guarantees for the norm of that self-normalized process. And in particular, we're after concentration inequalities that hold uniformly over time. And this is quite important in online settings and things of that kind. Okay, so we are after concentration inequalities that hold for light-tailed noises. And it turns out that if epsilon t is sub-Gaussian, then this problem is fairly well understood. However, what happens if epsilon t is not sub-Gaussian? So for instance, what happens when epsilon t fulfills a Bernstein assumption? So that is equivalent to being sub-exponential. Or what happens if epsilon t is bounded and hence sub-Gaussian, but we also want to exploit some information on the variance of epsilon t? So instead of having a Hoeffding type inequality, we want Bernstein type inequality. Okay, so now let me give you some motivation. Let's explore the classical setting, classical linear regression, where our Hilbert space is actually RD, and we have a set of y's and x's such that y depends linearly on x plus a Gaussian noise. Turns out that in this case, the least square, we can conduct inference on the least square estimate by multiplying it times xtx to the 1/2, and if we take the norm of that, that's gonna behave like a chi-square distribution. Now the question is, okay, what happens if our noises are not Gaussian or are not sub-Gaussian? And what happens if we're not interested only in giving a concentration inequality or conducting inference at one point in time, but we rather want to do it sequentially? And this is important for sequential decision-making problems such as linear bandits, kernelized linear reinforcement learning, and so on. Okay, so the intuition of our idea is actually very simple. We have the self-normalized process at time t, and we decompose it in two terms. The first term is fixed at time t. We have all the information, so there's no randomness. All the randomness appears in the second term through epsilon t. And now we're going to define this gt term, and we can see that the norm of the second term is going to be the same as the norm of gt multiplying the absolute value of epsilon t. So we're somehow decoupling the direction from the noise here. Okay, and for those of you familiar with the literature, I would like to mention that the sum of the square of the norms of gi's is upper bounded by 4 times the maximal information gain. And that's where the connection of our work with previous or related literature comes from. Okay, so the main theoretical contribution of our paper is a non-negative super Martingale construction. So for that, let me denote ET of lambda as the product of the square of the norm of GT times this conditional expectation of the exponential function of lambda times the absolute value of epsilon t, corrected by the first and 0th order term of the exponential function. So for those of you who are probably all of you familiar with the Chernoff bound and Chernoff method, we usually take the expectation of an exponential function. This is where that exponential function is kicking in. But because we're working with the absolute value, we have to correct it by subtracting the first and 0th order term of the exponential function. And based on this definition of ET of lambda, we can construct a non-negative super martingale, which is actually pretty interesting because we have a hyperbolic cosine part and an exponential function part. And the first time I came across these kind of non-negative super martingales, I thought they were beautiful. And the main reason why we have this hyperbolic cosine part in the non-negative super martingale is because we rely, or one of the key parts of our proofs relies on the machinery introduced by Joseph Pinellis in 1994, when he gave inequalities for the distribution of martingales in smooth Banach spaces. And we couple these ideas with the fact that the covariance matrix is always expanding over time as opposed to contracting. All right, so Diego, you've given me this non-negative super martingale. What do we do with this? So it turns out that when you have a non-negative super martingale, then you can derive a bunch of concentration inequalities. And in particular, the, I would say, general concentration inequality guarantees that we give in our paper is exhibited in this proposition, where we have that the norm of the self-normalized process is upper bounded by the sum of EIs of lambdas, this logarithm of 2 over delta, which is extremely common, divided by lambda. And the proof is immediate from the previous theorem. All we have to do is apply Wield's inequality, which is an anytime valid version of Markov's inequality, and upper bound the hyperbolic cosine by 2 times the exponential function. Okay, so that's great. We have a general theorem. What do we do with that? So I want to give you a tangible example, which is a Bernstein type concentration inequalities for the self-normalized process. And I would like to highlight that this problem has been addressed from several works and points of views, and I think it's a problem that we were going after for quite some time. So we're happy that we ended up with an actual Bernstein type inequality for self-normalized processes. So, okay, let me fix the n. So this is the ultimate sample size where we care about. And let's assume that epsilon I attains the Bernstein condition. If we have a constant Cn squared, such that that upper bounds the sum of the products of sigma I squared and the square of the norm of the GIs, then we get this maximal Bernstein type inequality for the self-normalized process. And in particular, I would like to highlight that if the lambda i's, or sorry, the sigma i's are constant across time, then it suffices to take this Cn squared as 4 times sigma squared times the maximal information gain. And again, this is where the relation with previous works stems from. Okay, and this will be all from me. I would just like to highlight that we have obtained rather general concentration inequalities. In particular, we get clean inequalities, known constants, small constants, which we're pretty happy with. I have not shown you, but we can also derive empirical concentration inequalities. So we have empirical Bernstein type inequalities for self-normalized processes. And all this that I've been showing you allows us to obtain regret guarantees for online learning algorithms in a very immediate or trivial manner. So the implications are pretty immediate. And that would be all for me. I thank you again for listening to me. And I promise this time is the last one.
Who's got questions for Diego other than Shai? Nobody? Shai? Okay, so I have to out myself as somebody who is profoundly scared of concentration inequality. So it's really as far away from my research as it gets within all. But it's something that I always wonder. I mean, I understand how useful they are, obviously, but what I don't understand really very well, and maybe you can enlighten me a little bit, is how limiting the conditions are, the premises of your theorem. For example, the last one you had this upper bound Cn squared on this, and I have to admit I don't understand really very well how limiting is this condition. Is it something that's that we could assume in practice, and when?
Yeah, it's actually a good question. Of course, there exist many different concentration inequalities. I think the main goal of why we started thinking about this problem is because we wanted a concentration equality for bounded noises, which I think is an extremely common assumption and intangible assumption. And so in that sense, many of the assumptions that I just explained carry through pretty much trivially in many settings. So, but yeah, it is true that depending on the setting, the assumptions may be extremely abstract or uninformative. Yeah. But generally speaking, I would say in this case, they are attained very easily.
Thank you.
So yeah, I'm going to present joint work with Shai. Happy birthday on no scale sensitive dimensions for distribution learning. So the question of whether distribution learning can be characterized by a combinatorial dimension has long been open. And we've given a partial answer to this by in the past by showing that distribution learning cannot be characterized by a scale invariant dimension. And in this paper, we solve the open question of whether it can be solved by a scale sensitive dimension. And we show that this actually is not the case. So we show that there cannot be any scale sensitive dimension that characterizes the problem of distribution learning with respect to total variation distance. So we are looking at a distribution learning setting. We get IID samples from some distribution, and we try to output a distribution with low total variation distance. And we consider both PAC learning and, in the scale sensitive case, weak learning guarantees. So this is very standard PAC learning setting. I won't spend much time there. So before looking into scale sensitive dimension, I first want to give a brief recap on what it means for a scale invariant dimension to characterize a learning problem. So intuitively, a characterizing dimension can be thought of as a set of properties of increasing hardness. And in many cases, these correspond to something like a class of size D can be shattered, and we have a countable set with D increasing over the natural numbers. So formally, we say a scale sensitive, as a scale invariant dimension is a countable set of properties such that a class is not learnable if and only if it satisfies all the properties in W. And then a structural assumption we want to make on these kinds of characterization is verifiability by finite evidence sets. So for every property and every class that satisfies the property, we want there to be a finite subset of the class such that every superset of this finite subset also satisfies the property. And this is, for example, also the case for shattering. You only need a finite number of functions in order to show that a set of a certain size is shattered, for example, VC shattered. So these two conditions are satisfied by all the things that claim to be dimensions that we were aware of. And in our previous paper, we showed that distribution learning cannot be characterized by such a dimension. However, we also showed in that work that regression learning cannot be characterized either by a scale invariant dimension. And we know that regression learning can be characterized by a scale sensitive dimension. So roughly what's happening here is that epsilon weak learnability does not necessarily imply PAC learnability. So we might want to characterize learnability for each scale of epsilon separately. And then we replace concepts like shattering with concepts like epsilon shattering. So instead of now having a set of properties W, we look at an epsilon specific set of properties, which is supposed to characterize epsilon learnability. So formally, we say we have a set of properties W, which decomposes into W epsilons. Each of the W epsilons is a countable set of properties. And now we allow for a slack factor. So we say if a class satisfies all the formulas, it's not epsilon weakly learnable. And if there exists a formula that a class does not satisfy, then it is at least C times epsilon learnable. So that there's this factor C. A good characterization would have a small factor, but sometimes there is maybe a gap of knowledge which we allow for. And we still keep the finite evidence property from before. And the main theorem of our work is that the task of distribution learning cannot be characterized by a scale sensitive dimension for any possible slack factor C. So there's no room to squeak something with the C. And the proof is rather simple, so I will try my best to get it done in the time we have before the break. So one simple lemma is we can show that if we have a learning task that is characterized by a scale-sensitive dimension, then if we have a class that is not C times epsilon weakly learnable, there exists at least one countable subclass that is not epsilon weakly learnable. So this kind of is similar to compactness. We call it countable compactness in the paper. And this is very easy to prove. So we start with a class that is not C times epsilon learnable. We know that it has to satisfy all the properties in the set W epsilon. And now from the finite verifiability, we can take all the finite subsets, take the union. This is a countable set. This countable set now has to satisfy all the formulas in W epsilon. And therefore, by the second property of scale sensitive dimension, this countable class is not epsilon weakly learnable. So this gives us a way of knowing what to look for in a counterexample, and Shai and I like counterexamples, so that's what we did. So we constructed a class which is not epsilon weakly learnable for any epsilon, but every countable subclass is Pak learnable, and it's like Pak learnable very easily. So I will give the construction. So for a number D, we consider the ball with radius 1 around a point, like the d-dimensional ball around point 3D. And then we take intersections with d-1 dimensional hyperplanes. And we look at the set of, and then we take those sets and look, consider uniform distributions over the set. So for d equals 2, it looks like this. We take a ball, and then we take all these d-1 dimensional subsets. Now, and then we just take those classes D and take the infinite union over those. Now, one thing we can see is that even if we are in the same ball, all of the distributions, like all the supports, only intersect on sets of mass 0. So for every two sets B of the same of the same dimension, their intersection is a d-2 dimensional surface. So it has mass 0, and otherwise, otherwise they don't intersect. So we get that any two distributions in this class have total variation distance 1 from each other. And furthermore, if we take the support of any distribution Q and we measure it by P, that measure is 0. And now if we take a countable subset, we can look at all the supports of the different different distributions, take a countable union over those, and that has still measure 0. And therefore, when we get one sample, then with probability 1, this is in a part of the domain that is unique to this probability distribution. So we can perfectly identify it, and we have a sample complexity of getting epsilon and delta down to 0 with one observation. On the other hand, this class is not learnable. So given a sample size m, we can take the subclass dm plus 2. And then we look at a uniform meta distribution over this class. Now we take so basically we now randomly sample a distribution from the subclass dm plus 2. And then if we take a sample of size m from that, we know that it defines an m minus 1 dimensional hyperplane. But all the, so there will be an uncountable number of consistent candidates in the set dm plus 2, because all the distributions in there are distributions over m plus 1 dimensional surfaces. And then we can show that for any learner, the expected distribution distance from a randomly sampled distribution is 1. So this is not learnable with respect to any epsilon. So we get a very strong separation between the countable subclass case and the class itself. And from this, it follows our result directly follows. We also have some nice we also draw some nice connections between the compactness of the sample complexity and show some positive results for our notion of scale-sensitive dimension. In particular, we show that countable distribution classes over countable domains can be characterized by a scale-sensitive dimension, at least the way we define it. But the caveat here is that we defined the notion to include everything to give a negative result. So the main result of our paper is the negative result. And I'm happy to talk about the positive results in the poster session. I don't think I have time for it. Thank you.
Thank you very much, Tosca. Who's got questions for Tosca? First.
Thank you. So your results here are for the total variation distance. Do you have any idea if there's such a dimension here for other metrics like the Wasserstein metric?
We haven't looked into it. The Wasserstein metric, does it? So it doesn't hold for KL divergence for sure. Yeah. Like we know that. We haven't looked into Wasserstein metric, but yeah, maybe we should.
Okay.
Szymon, you all.
So do you think that there could be another way to define dimension that doesn't rely on finiteness of evidence? Or, well, we want the evidence to be finite, but maybe it can be finite in the way of a finite logical formula, for instance, and not as a finite witness set. Would that help?
So the finite evidence property is actually something that kind of is an implication from a different formulation, which was said to be, we want this to be first order formulas. And then we can use compactness of first order logic to get the finite evidence properties. So our definition also includes all first order formulas. So you would have to go beyond that even. But there can certainly be other types of characterizations potentially, but I think this is very, I feel like it's very strong in the generality.
any further questions or? Well then, thank you again, Tosca.